Let's talk about sources. So just like we had the basic elements of resistors, capacitors, inductors, we also have basic sources, primarily voltage and current sources. So we're going to think analogs again. So you think of a water source as, delivers water, current source delivers charge, and a 1 amp current source would deliver 1 coulomb of charge per second. So this should be, I think, very understandable, and yet I think probably in your physics course you never talked about current sources. You more likely talked about voltage sources, which I think in a way is a more abstract thought than a current source. But a current source will be one of the types of sources that will be very common in circuit analysis, and so we start with it. Okay, so with the current source, the load, that is whatever that's attached to the current source, has no choice but to accept the charge that is delivered, regardless of how resistive it is to the charge. The greater the resistance of the load, the greater the voltage response across the load, right? So the source is going to say, I'm going to give you 1 coulomb of charge per second, whether you want to take it or not. If you resist me, I'm just going to put more effort, just more volts. Okay, so a voltage source, on the flip side, is really a potential energy source. Okay, potential energy source. We talked about this already. A voltage source, a 9-volt source, guarantees 9 joules of potential energy per coulomb, regardless of how rapidly charge is required from the source. So this is analogous to a water pressure source, where water is supplied at some fixed pressure, say 50 pounds per square inch. And it doesn't matter whether you're asking for 1 gallon or 20 gallons or 100 gallons a minute. Now we experience what a poor pressure source is with our garden hoses. So you've noticed before that if you ever have had a long garden hose, and you have a sprayer on the end, when you first pull the trigger on the sprayer, you'll get a lot of water coming out, but after a little bit, that water flow diminishes. Well, actually, the hose, which is a bit compliant, kind of rubbery, it can actually expand a little bit, and it's like a capacitor. It's a little reservoir, and so it's able to give you a lot of that water initially. It's stored in the hose, but eventually all of that water has to be coming from the house and from the well, or from the city, and so there is a pressure drop through that hose, and so we don't have an ideal pressure source. Even though if you stop the flow and you put a pressure gauge on your water, at the end of your water hose, you would measure 50 psi, whether it was measured there or whether you measured it back at the spigot. As long as there's no water flow, it'd still be 50 psi. But once water starts flowing, that pressure drops. So we'll talk about ideal sources, which are non-existent in the real world, but there are sources that are close to ideal, at least within the confines of a particular application or use of that source. So we can say, well, this source, from the vantage point of this type of load, this source really does look like an ideal voltage source or current source. Okay, so just two examples here. So first, voltage source. A 9-volt source always delivers each coulomb of charge with 9 joules of potential energy. So if for a voltage source to deliver more power, it must supply more coulombs per second. In other words, more current. If you want more power out of a voltage source, then you just need to ask for more current. At 1 amp, you're going to get 9 times 1 coulomb per second, or 9 watts. If you want 900 watts, then you've got to pull or extract 100 coulombs per second to get that higher power. For a current source, it's the flip. If you have a 2 amp source, you're always going to deliver a fixed rate of charge. You get 2 coulombs per second. But if you say you want 10 watts delivered, then you would make that source deliver that 2 coulombs per second into a 5 joule per coulomb voltage, okay, 5 volts. So in other words, you have your current source here, that's 2 amps, and then you're going to deliver it into some load which is going to produce 5 volts. So that would be like a 5/2 of an ohm would do that, and that would deliver that current going through there would produce 5 volts, such that now 5 volts times 2 is 10 watts. So that resistor would be receiving 10 watts. If you, the resistor, now wanted to have not 10 watts but 100 watts, you would have to change this resistance to 50 over 2, or 25 ohms, because you would need 2 coulombs per second times 50 joules per second to get your 100 watts. Okay, so the point here is that with a voltage source, the way you get more power out of a voltage source is you ask for more current. The way you get more power out of a current source is you make that current source deliver its charge into a higher voltage. Okay, so here is a voltage source and a current source. We have them together, and I show some symbols. So it could be the battery, it could be several cells, battery cells stacked, or just the circle with the plus and minus. Any of those are equivalent. You will always have a voltage next to it, whether it's a number or a symbol like VB or VS, which now is the variable that would represent the voltage. And just like we have a VI relationship, the constituent relationship for like a resistor, a capacitor, or inductor, we can have a constituent relationship for the voltage source. And as a reference point here on this graph plotting voltage versus current, I have drawn a dashed line showing the relationship, VI relationship for a resistor, right? Straight line. And in this case, because it's volts versus current, the slope is actually R, resistance. Okay, so that's for a resistor. But here we're talking about a voltage source. What does the VI relationship look like for a voltage source? Well, by definition, a voltage source puts out a voltage. And so if we have a voltage source VS, and let's say VS is 9 volts, then this is 9 volts. And we can say that a voltage source will have a voltage 9 volts regardless of how much current you demand of it. So if there's no current, it would put out 9 volts. If there's 1 amp flowing into it, it puts out 1 volt. If there's minus 1 amp flowing into it, it puts out 9 volts. So it turns out that the curve, or the line for the VI line for a voltage source is just a horizontal line. Okay, in this case where I'm doing voltage versus current. The opposite is true for a current source. So here for a current source, I'm again plotting V versus I, but here we have a vertical line, which says, let's say this current source was a 2 amp source. So if you demand, if that current source is going into a short, then there's no voltage across it, 0 volts, but it still puts out 2 amps. If you make it work into a plus 1 volt source, then it still puts out 2 amps. If you make it work into a minus 1 volt source, it still puts out 2 amps. So you get a vertical line. Notice the 3 symbols here. We'll usually use this one on the left, circle with an arrow through it, but I just wanted to point out the other 2. You can have 2 off-centric circles. That is another symbol for a current source. Okay, in this example here, just I'm highlighting how very different the power delivered by an ideal source will be based on what the load is that's connected to it. So in the first case, we have a 2 amp source that is delivering 2 amps through R1, and the power delivered to that resistance is just going to be I squared R, right? I squared R. So I squared is not going to change. It's 2 amps, so it's 2 squared, or 4. And then it'll be 4 times whatever R1 is. Well, if R1 is 1 microohm, then this source will only have to deliver 4 microwatts. But if this source is 1 megaohm, then this 2 amp source will have to deliver 4 megawatts. And the reason is that when you push 2 amps through a 1 microohm resistor, it only develops 2 microvolts. So that's what the source has to work into. But when you push 2 amps through a 1 megohm resistor, you get 2 million volts. And now the source has to push 2 amps through up 2 million volts. Okay. The same, or similarly, is the case for the For the second resistor, here we have a voltage across it, a voltage source, so I've written the power to the resistor as V squared over R. So now we have 4 over R. And again, if we have 1 microohm versus 1 megohm, we have very different power. Now notice that they're flipped. In the first case, if you have a very small resistance with the current source, the source doesn't have to do any work, right? Because asymptotically, a short there means no voltage, and therefore no VI product. It's the opposite for the voltage source. Look here, if we use R2 is 1 microohm, and we do 2 squared over R, 2 squared over 1 microohm, we end up getting 4 megawatts. So a 1 microohm resistor in R2 there will actually absorb 4 million watts. And that's because the current that is going to be flowing in that case will be 2 volts divided by 1 microohm, or 2 million amps. So that results in the high power. If R2 is 1 megohm, now the current flowing through it is just 2 volts divided by 1 megohm, or 2 microamps, and that results in the 4 microwatts.